Hello, we're back in my office at Caltech in Pasadena, California. And this mini lecture has a rather simple message. It's that the major language of the nervous system is the frequency of a neuron's action potentials, or nerve impulses. Each individual neuron sits in its own circuit, has its own inputs and outputs, its own way of processing data, but we can summarize that neuron's activity in most cases by the frequency of nerve impulses. And in many cases, the effects of drugs are revealed by changes in the frequency of a neuron's action potentials. Here is an experiment from my friend David McCormick, Professor David McCormick at Yale. This is an experiment on a brain, an intact brain, that has a microelectrode stuck into a neuron in that brain. This microelectrode is recording the difference between the intracellular and the extracellular solutions, and that's a voltage difference. And David McCormick is also able to pass current, so V and I, through that same electrode. V is voltage, I is current. Furthermore, as you'll hear in a while, in addition to measuring the voltage across the membrane and commanding the current across the membrane, David McCormick has also led the voltage signal to the audio track of this recording, and so we'll hear little clicks, pop, 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 each time we get an action potential. The experiment takes about 21 seconds. The neuron starts off without a real resting potential because there's no straight line here. Then David McCormick passes some current through the electrode, depolarizing the neuron, changing it, making it less negative, more positive. We get a higher frequency of spikes, although there's a no man's land in between, which is quite interesting. And then David McCormick takes the current away, and we go back to a low frequency of spiking. So let's watch the experiment as it was recorded. So we see that here we have a frequency of about 3 impulses per second. Here we have a much higher frequency, several tens of impulses per second, and they can't clearly be resolved on this trace, although you could hear a buzz, a flurry of impulses. There are other interesting aspects to this trace. For instance, in the more negative part of the trace, there are these broad bases to the spikes. Well, these broad bases probably actually trigger the spikes in the first place, because here's one that's not quite big enough to trigger a spike, but the broad base is occurring anyway. When the cell is at its faster firing frequency, at its upstate, professionals call it, there are not these broad bases. There is a little bit more noise here than in the downstate. There are lots of interesting aspects of this experiment. The important point, though, is that by controlling the current that we pass across the membrane, we can control the firing frequency, and that the firing frequency is the most important message that one neuron sends to another. So let's watch this experiment again. Well, that experiment you can replay if you'd like. Let's go on to the next one. In this next experiment, we're again David McCormick and his colleagues are again recording between the inside and the outside of a neuron. This neuron has acetylcholine receptors, not the nicotinic type that we've been discussing in previous mini lectures, but a muscarinic type. And here David McCormick and his colleagues are adding acetylcholine to the vicinity of the neuron. Although there's a dropper here, you should, of course, note that there's a solution bathing the cell all the time, and it's actually more like a squirt than a drop coming out of this other pipette. And so, as though the presynaptic neuron were adding acetylcholine, the experimenter is adding acetylcholine here. It's the same kind of thalamic neuron that was on the previous slide. These thalamic neurons relay information, as you learned in previous lectures, from the periphery to the cortex. And so let's watch how muscarinic stimulation changes the frequency of this relay. It's going to be a little bit more difficult to see this one because it's on a 20th century oscilloscope, and you'll see the trace glowing, and you can't quite see the spikes so well as on the previous trace, but because you saw them very clearly on the previous trace, you can get a good idea of what's going on. Now David McCormick is adding the acetylcholine. So you saw the traces, the spikes now as sharp upswings in the trace. You saw the cell firing repetitively, but at a rather low frequency before the acetylcholine was added, and at a higher frequency afterwards. Let's watch that again. So what do we learn? We learn that drugs can do things that other neurons can do, that we can perturb a neuron's firing frequency, that most important aspect of its function with a drug, in this case acetylcholine, and with many other types of drugs. And we learn, of course, that electricity is the language of the nervous system, and that in particular, the frequency of impulses is vastly important. Well, there are actually a large number of techniques that neuroscientists have developed and utilized over the last decades in order to measure the activity of the brain. And here is a summary of them all. And the key aspect of this plot is that it summarizes the size of the brain area that can be studied with one technique or another, and also the time scale that can be studied with one technique or another, and also the degree of invasiveness of that technique. And so you can see that there's not much empty space on this map, and this is why neuroscientists like to say, when one thinks about psychology or emotions, they say, well, we can study that. In fact, if it goes on in your head, a modern neuroscientist can study it. So at the least invasive part of the scale, we have magnetoencephalography and event-related potentials. These are done with either a magnetic sensor or electrodes near the scalp. We have functional magnetic resonance imaging, fMRI, which is done in a large magnet. It's not terribly pleasant, but it's not very invasive compared with intracellular recording. Positron emission tomography is also not very invasive. Lesions, if they happen to have been caused accidentally or by illness, don't require further invasiveness. So we can go all the way from nearly as fast as a millisecond to many days. In fact, in this case, let's see, 10 to the 7th seconds in a year. So years, lesions are stable. But we don't get very good spatial resolution with these non-invasive techniques that can be applied to whole animals and living people. If we want to record events on a much finer distance scale, we need to use the kinds of intracellular electrodes that we saw on the previous slide, or patch electrodes. There are now ways of recording lots of activity at once with sets of electrodes, or even with devices with silicon arrays. So again, we can't go into all of these techniques in this course, but I can assure you that each of these techniques has been useful for unraveling the effects of drugs on the brain, and we'll try to give some of the examples of this as the course goes on. So I look forward to teaching you about how we apply modern neuroscience and modern neuroscience techniques to drugs and the brain.